Hi, everyone. Thank you for the organization of the meeting and for allowing online participation. I present long-running work on the parameterization of tidal mixing. So this involves many colleagues who are listed here. And the overarching goal is to build a parameterization that is comprehensive, energy constrained, and also applicable to ocean general circulation models. So I'm first going to briefly describe the parameterization, how it's constructed, then show some comparisons with observations of mixing, and finally show some results with the NEMO global ocean model. So an introductory slide, probably not needed for this audience. But briefly, when you have an oscillating tidal flow impinging on sloping topography, this displaces the isopycnals, creating waves that we call internal tides. And these internal tides can be either relatively small scale, and then we call them high modes or high vertical modes. And they tend to contribute to relatively local mixing. Now, there are also some internal tides that are quite large scale. We call them low modes, and they're less susceptible to instability, and they will tend to contribute to mixing far away from the generation sites. At the bottom here, you have a transect of diffusivity from Paulzin and colleagues, 1997, that kind of illustrates these two types of mixing. So you're looking at diffusivity in centimeters square per second along this transect from, say, the coast of Brazil, down the continental slope, and then up the mid-Atlantic ridge here. And the elevated diffusivities that are above the rough topography of the mid-Atlantic ridge, we know they are due to locally generated high mode internal tides. And that mixing has long been parameterized in ocean models. But there's also a more distributed, more uniform mixing elsewhere. And that mixing is actually largely due to low mode internal tides that can come from elsewhere and that ultimately cause mixing. And that mixing is usually not explicitly parameterized in ocean models. And so this is partly why we wanted to build a comprehensive parameterization that does both the local and the remote mixing. So the methodology is summarized by these slides. So we're doing a mode by mode tracking of energy from sources to sinks. So it's essentially ray tracing or beam tracing, and it's inspired by the ID mix concepts put forward by Olbers and Eddy. So the first step is to create some static 2D maps of depth integrated dissipation. And this is done with an observational climatology of stratification. So we took the WOS climatology, which is 1/2 a degree in horizontal resolution. So we start from maps of the generation rate of internal tides, decomposed into vertical normal modes. So we have the generation rate for each mode. We infer that modes greater than 6, they don't really propagate outside the source grid cells at our resolution. And so this energy moves directly to the dissipation. But the first 5 modes, they do redistribute energy and cause some remote mixing. So we track their energy with a Lagrangian scheme. And using observation and theory, we estimate the dissipation due to critical topographic slopes, due to shoaling onto the continental shelves, due to wave-wave interactions, and due to scattering by abyssal hills. So at this stage, we have 4 static 2D maps of the depth integrated dissipation, each due to a distinct dissipative process. And so what we now need to have a 3D distribution of power input to turbulence and a 3D distribution of diffusivity ultimately is to distribute this energy in the vertical. And so we then apply some vertical structures for each map that depends on stratification. And if you're applying this parameterization in an ocean model, then it depends on the evolving stratification of the model. Now, I just want to insist on the importance of using the Lagrangian framework for the beam tracing, because we first started with an Eulerian framework, and we were not satisfied. And this is illustrated here. So you're looking at the energy transport by the mode 1, so the first mode, M2 internal tides. And so you see the beams. The top plot is the Lagrangian calculation that we made. And so you can see the beams traveling across basins. And at the bottom, you immediately see that the beams are really diffused very quickly. And this is because the advection in an Eulerian framework necessarily spreads the energy in the angle and so you get this radial spreading very, very fast away from the generation sites. And you may also notice that the beams that actually stay beam-like are only those that have a direction that is aligned with the grid. So it's east-west beams, north-south beams, and also the diagonal in the diagonal directions. These are the beams that actually are fairly well maintained, and it's just because they are aligned with the grid. So the Eulerian advection or Eulerian propagation of energy diffuses the beams, but also diffuses more the beams that are not aligned with the grid, which is why we move to a Lagrangian framework. So this is the result of this method. Basically, we obtain these 4 static 2D maps of depth integrated dissipation. This is shown in log scale here. So the 4 maps are very different patterns and energy levels. You have fairly strong and fairly distributed mixing at the top left. This is wave-wave interactions, about 60% of the energy. On the top right, you have dissipation on the continental shelves mostly. So this is shoaling. At the bottom left, dissipation mostly at the steep continental slopes. This is the dissipation due to critical slope interactions. And at the bottom right, you have dissipation mostly above the rough mid-ocean ridges, and this is the scattering by abyssal hills. So these are the 4 maps we have, and then we need to distribute the energy in the vertical. So we simply use a vertical profile that's proportional to n squared for the wave-wave interactions. N is the buoyancy frequency. For the shoaling, it's proportional to n. The dissipation at critical slopes is really intensified at the bottom, so it's an exponential decay with height above bottom. HAB here is height above bottom. And at the bottom right, it's only slightly more complicated. There is a fraction of the energy that's bottom intensified, and another fraction that scales with n squared. So that's the parameterization. Then there are 3 parameters in there that are constrained by the observed topography and by the comparison with microstructure data. So I'm moving now to the comparison of the parameterization with observations of mixing. So we gathered the microstructure data. So it's summarized here. We have 19 different projects, about 1,200 profiles of measured dissipation. And what we're going to do first is to make an average profile for each of these projects and compare this average profile to the profile predicted by the parameterization. And I'm showing here 10 projects as an example. So these are profiles of dissipation or power input to turbulence, if you want. And in black, it's the microstructure data. In blue, it's the parameterization. And so I'm not going to go in detail to each project, but basically you see that the parameterization seems to get reasonably well the vertical structures and most often the energy levels. But there are clearly discrepancies. For example, at the bottom right, you have the 3 Southern Ocean projects where the discrepancies are more significant. And this is probably because the Southern Ocean has not just tides, but many other phenomena that create mixing. A more visual comparison is this one. So I'm actually looking again at the Brazil Basin. So at the bottom here, you have the same data I showed in the introduction. but now you're looking at the dissipation in log scale. So these are a bunch of microstructure profiles taken again along the Brussels Basin towards the crest of the Mid-Atlantic Ridge. And at the top, you have the same transect predicted by the parameterization. And in general, what you find is that the parameterization does a fairly good job at reproducing the contrast between the eastern and the western Brussels Basin, and also the contrast between the abyssal and the upper ocean. Now, more quantitatively, if you take the 3D distribution of microstructure data that we compiled, and you compare it with the 3D distribution of the parameterized dissipation at the same locations, you get this scatter plot, or this 2D histogram here, which shows that you have a reasonable agreement given the patchiness in the data over a few orders of magnitude, a good correlation when you take the values in log scale, and basically 85% of values agree within a factor of 10. We also compared with less reliable but more extensive estimates of mixing, which are called fine structure estimates. So we have two data set, Kunze 2017, which is ship-based CTD data, and then Whalen et al. 2015, where the fine structure method has been applied to Argo CTD data. So we did this comparison, and again, the scatter plots show that we have a good correlation across at least 4 orders of magnitude, with almost 90% of the data agreeing within a factor of 10. So we're reasonably confident that we are producing realistic distributions of mixing. So the next step then is to apply this parameterization in an ocean general circulation model. So the advantages are the following. It's quite cheap computationally because you just have to read 2D maps and then distribute in the vertical the energy. The mixing distribution is quite realistic, as we just showed. By construction, it's energy constrained. And finally, the vertical structures are interactive. And we know that vertical structures is perhaps the most important ingredient in such mixing parameterizations. Now, the drawbacks are, of course, that the 2D power maps are static, and so they're not interactive. They don't evolve with the ocean state. And also, they are based on the modern ocean states. So overall, this parameterization favors the realism of the distribution over the interactivity. And this is okay for a climate change scenario. We tested the assumption that the horizontal power maps will not change much over a few centuries, even if there is a very, very strong warming. But of course, it's not applicable directly to a simulation of the last glacial maximum, for example. And I guess the bottom line is that static 2D power maps are better than static diffusivities. Because if you apply a static background diffusivity, you don't control the energy that you feed your model, and you know that you don't have a realistic response to changing stratification. Now, I'm going to show just a few quick results of the implementation in NEMO 1 degree. So it's a 1 degree global configuration of NEMO that we've run for 1,000 years under core 2 normal year forcing. And we have 3 experiments, one with the old style parameterization of tidal mixing, so only local bottom intensified tidal mixing and a background diffusivity, which is constant. And this creates the power that you see at the top. So this is the depth integrated power that feeds mixing in the model. The middle map is essentially the parameterization I described. So we call this experiment new. And so this just includes local and remote tidal mixing explicitly, as I just described. And finally, the last experiment is the same as new, but has the added contribution of trapped or subinertial internal tides. So here we just added an estimate of the dissipation due to subinertial internal tides, which are important in the polar regions. You may see that around Antarctica and in the Arctic, you have more energy in this lower map than in this middle map. So the three simulations have different distributions of energy and mixing. It's much more heterogeneous in space when you have these more comprehensive parameterizations. But actually, if you integrate the energy along a latitude band, you get these three profiles, which look very much alike. So essentially, the energy is distributed in a similar way on basin scale, which is partly why the impacts on circulation and stratification are relatively modest when switching from one scheme to the other. Now, there are some differences at high latitudes. And when you include remote tidal mixing, you get stronger NEW formation. And you have more energy basically in the North Atlantic in particular. And when you include trapped internal tides, you have much more energy in the southern high latitudes, and you have stronger ventilation of Antarctic bottom water. So this is illustrated very quickly in the next two slides. Here I show the Atlantic MOC simulated by the model after 1,000 years at 26 north. So the red is the rapid observations, and the black is the old parameterization, and the blue lines are the more recent and comprehensive parameterizations. So basically, you observe that we get about 1.5 Sverdrup more AMOC in the new and TRA experiments. And a last slide to illustrate the ventilation rate. Here I show the zonal mean ideal age at year 1000 in the TRA experiment for the Pacific at the top and the Atlantic at the bottom. And then we have the difference between TRA and new in the middle, and the difference between TRA and old on the right. So basically what this shows is that the addition of trapped internal tides increases the ventilation in the deep Southern Ocean and the abyss. So we get younger abyssal waters. And the rightmost plots show that when you have a more comprehensive tidal mixing, you get a stronger and deeper AMOC, and so also higher ventilation at mid depths in the Atlantic. Here is the summary. So we constructed a global 3D map of internal tide-driven mixing, which is available online, which has many, of course, huge uncertainties, but a fairly encouraging comparison with observations of mixing. We implemented this parameterization in NEMO. It has overall a modest impact on circulation stratification when compared to the scheme to the older scheme I described. But it has an important impact on ventilation rates, and we expect on biogeochemistry. Now, there are many other applications of this parameterization, including water mass transformation estimates, inverse modeling, and biogeochemistry budgets. Thank you.
Thank you for the talk, Casimir. I have one question. You said that the modeling of the tidal beams with the Lagrangian scheme is more, or yields better results than with the Eulerian scheme. It's of course dependent on the grid of your Eulerian scheme. Then I guess that depends on the grid size then. And second, what we saw, for instance, from Peter's talk, that there's a lot of variability in these beams, right? By scattering or refraction by mesoscale eddies, such that you wouldn't expect to have a straight beam across the Pacific. So what do you think, what would be the impact of a little bit of scattering or refractions in these beams on the scheme?
Yes, so these are two very, very good points. So you can definitely reduce the sort of numerical spreading of the energy if you increase the spatial resolution, or if you have a refined, potentially a refined or different grid, different type of grid. But you will always have some, of course, some numerical spreading. And in particular, one of the issues is that you need to have an angle resolution when you propagate these beams. And if you increase the angular resolution, often because of refraction as you propagate the beams, you tend to actually increase the diffusion in angle. So the resolution increases are not complete and straightforward solution to the diffusion thing. Now it's clear that in the reality there's a mesoscale eddy field that spreads the beams. So I showed an extreme case where the sort of energy was really confined in one angle, so that you really see the signature of the beams. But in practice, in the reference maps we constructed, we chose to distribute the beams at the source in a reasonable way, but a rough way, to have sort of implicitly the effect of scattering and interactions with a variable eddy field that will distribute the beams and change their angle. And so this is clearly not explicitly represented in the scheme. It's only treated in a very rough, imperfect way. And I know that Friederike is going to talk more about the direction of internal tide generation and these aspects.
Hi, thanks for the talk. Maybe after my talk, the obvious question. What's the potential of this, of applying this method in an online scheme, in the sense that one would diagnose the sources directly from in the model online, calculate the redistribution in time, and then use this to estimate the dissipation online, because it would take care of a range of problems that you've mentioned, but also what Carsten has talked about.
Yes, exactly. So that's possible, and that's what a bunch of groups are trying to do, is to do it online, and it's entirely feasible, including doing a Lagrangian calculation online. You can do this, but it has a cost. It has a cost, of course, a computational cost, but also we found that the advantage of doing this calculation offline is to be able to do a more detailed estimate of the energy sinks as well. Because, for example, the interactions with topography, they are fairly involved, they're fairly complex. And so in an offline calculation, we could be much more detailed than we would be able to do online. So it's basically the two reasons: being able to do a good Lagrangian propagation and an accurate dissipation, that motivated us to do it offline. That said, it's possible to do it online, but there's going to be a cost, a computational cost, and also a reduction in accuracy probably in the way the dissipation is estimated.